Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's a great pleasure to welcome Maria from University of Southampton. She's the last of our external speakers, and she's going to tell us a little bit about social dilemma. So, Maria, thanks for coming, and over to you.
Yeah, I'm probably going to tell something that game theoretic solutions can be not that bad at predictions behavior if you come up with the right solution concept. Anyway, yeah, so I'm going to introduce the concept of cooperative equilibrium to predict behavior in social dilemmas, in particular those played in iterative setting. This is a joint work with Valerio Capraro, Matteo Venanzi, and Nick Jennings at the University of Southampton. Well, the first prediction I can make right now is that this talk probably will take less than 45 minutes. Let's see. All right, so the standard assumption that economic models make of that players always act perfectly rational have been assessed implausible in many experimental studies with human players, and these studies usually are conducted with on fundamental social dilemmas such as the prisoner dilemma, the traveler's dilemma, and the public goods game, in which high rate of cooperation have been demonstrated, and by cooperation we mean here the deviation of the unique but inefficient Nash equilibrium in these games. And it's also been shown that the rate of the cooperation was dependent on the game parameters, the pair of function parameters or the other parameters in the game, or the environment in which the game is played, how the players are matched to each other, and so on. How frequent is the interaction between different types of the players, and these type of things. So let me just briefly remind you, if you've forgotten, which is hardly to believe, the prisoner's dilemma. You have two players, two prisoners separated by a wall, and they can choose either to cooperate or defect, in which case, if both of them cooperate, they get a reward R, and if both of them defect, they get a punishment pay of P, which is lower than the reward. If one of them cooperates, he gets a temptation payoff of T, which is the highest of all. And if, if one of them defects, he gets that, and the cooperating player in that combination gets a sucker payoff of S, which is lowest of the all. And it's known that there is a unique Nash equilibrium for both of the players to defect, and of course it's not the best thing to do because it's not there is a Pareto optimal solution for both of them to cooperate and get a better payoff. Similar situation we see in the traveler's dilemma. We have two travelers. They can claim some amount xi within the range of L or H of monetary units for their luggage that have been lost by the same airline company. And the airlines have the rules to avoid high claims, so that the traveler with the lower claim, M, would get M plus B units. The other one will get M minus B units, where B, the value of the bonus of the penalty, is fixed. And if both claim the same amount, they will get the very same, that amount. And once again, in this game, it's obvious that the unique Nash equilibrium is to claim the lowest possible amount of money, but it would be the best thing to do for both of the travelers to claim the highest reward, highest reimbursement. And finally, the public goods game, we have N players in this setting. Each one has some endowment of monetary units, and they can contribute some amount of money to a public pool. The pool then is multiplied by a constant alpha 0, and then evenly divided among the players, so that the utility of each player is his endowment minus his contribution and some fraction of the total amount, where this fraction is called the constant marginal return. That's it. The unique Nash equilibrium here is to contribute 0 to the public pool, while, of course, everyone understands that it would be better to multiply our money altogether. And well, people do understand that. So in practice, in many experiments that have been conducted, cooperation is frequent, and basically it depends on the parameters or the environment in which the game is played. In Prisoner's Dilemma in particular, the rate of cooperation would depend on the payoff function parameters or the way the players are matched to play with each other, and there are several works that shows these dependencies. In Traveler's Dilemma, the rate of cooperation depends on the value of the bonus penalty B whenever the game is single shot or iterated. And in the public goods game, the rate of cooperation depends on the value of the marginal return, the main parameter of the game, and also on the frequency of iteration between the cooperators or free riders based on the previous iterations of the game. Now, the three references there which are highlighted are particularly relevant to our work because they, they use iterative settings, and also basically we use their experimental data for our calculations. And I would like particularly to thank Anna Gunther-Dottir for the original data that she sent us that was not included in their paper. Okay, so all these findings actually inspired a considerable effort in attempt to explain the observed behavior of human players. Some methods in this direction assume that actually humans just have bounded rationality and makes mistakes in their computations. And there are key paradigms in this direction: the quantum response theory, the level K, the quantum level K theory. The drawbacks with this approach is that it's really hard to justify this point of view for the games where the payoff function is actually easy, like in Prisoner's Dilemma, or where the incentive for deviation from a Nash equilibrium is obvious, like in Traveler's Dilemma with the penalty close to 0, right? Other methods explain cooperation in terms of evolution. One of the examples here, the cognitive hierarchy model or reciprocity mechanisms, but they actually have been shown to be outperformed by the quantum level K theory, so they don't seem to predict the behavior very well. Finally, lots of work has been done in attempt to define just profoundly different solution concepts. And here we have the notion of fairness equilibrium, the fat-sided pre-equilibrium. Both of them, although predict either complete cooperation or complete defection in the Prisoner's Dilemma, so they're quite rigid. Another notion is that of maximum perfect equilibrium. This was shown to be quite good in many settings, but in Traveler's Dilemma, it predicts cooperation irrespectively of the value of the B. So it's also not very flexible. Then the iterated regret minimization showed good performance in many settings, but once again, it showed, it coincided with the Nash equilibrium for the Prisoner's Dilemma, so it didn't predict cooperation there at all. While the COCO value, on the other hand, predict full cooperation in the Prisoner's Dilemma. So all of these notions are not flexible in all the dilemmas they've been applied to. So based on this, recently another concept was proposed. This is the work of Valerio. So he came up with the idea of cooperative equilibrium that he defined for the single-shot games. And the idea is as follows. Why don't we believe that actually humans have natural attitude for cooperation? So basically, they start playing not as single players, but they would assume that they would form coalitions. And then they would forecast how the game would have been played if they formed coalitions. And they take actions according to their best forecast. So this is just the essence of this idea. And it demonstrates actually impressively high precision when it's directly implemented for the single-shot games. What we do here, we just extend this approach to iterative settings. Right. So we define the iterated cooperative equilibrium that combines this approach with some ideas previously developed for iterated games. And what's important here that in contrast with other methods, the iterated cooperative equilibrium doesn't use any free parameters, so it's fully predictive. So we evaluated on the traveler's dilemma, on the prisoner's dilemma, and the public goods game, and we show that it makes quite accurate predictions. For the traveler's dilemma, we also compare it to the logit learning model that was developed in the original paper with the experimental data, and we show it outperforms that model as well. Okay, I have to define it. So a bit of notation. So we take we're in the normal form game with set n of n players, Si few strategies and Ui are utility functions for each player I. We look at the mixed strategies and the expected payoffs defined in a usual way. And the idea behind this notion is very simple. So identify yourself now with the player I and just look at the game from the perspective of player I. So simply consider two possible situations, two possible scenarios. Either all players are completely selfish, so it's a fully selfish play, we call it PS, where everyone maximizes or optimizes his own interest, his own utility. Or all players are fully cooperative, so they pursue the collective interest. Now, with each scenario, we associate a value, VIP. Well, actually, index I will go through the whole slides now, which is just an average with the following probabilities and values. So tau of P is the probability that all players actually do play the scenario P. And tau bar P is the complement probability that they do not play that scenario. But what do we mean by they do not play that scenario? This means that at least one of the players deviates from that scenario, pursuing his individual interest. So these are unilateral deviations, not collective deviations. And this basically means that for this scenario PS, this probability is 0, right? Because players would play just Nash equilibrium, and there is no unilateral incentive to deviate for any of them. Now the payoffs are, so the E of P is the payoff where the players play the scenario P, so either in Nash equilibrium or the cooperative play, and the payoff to the agent I where there are deviations is given by the infimum of his gains where other players deviate from that scenario. Okay. We now use these values to determine the strategy of each player in the cooperative equilibrium. So we look at these two scenarios. We take the one that maximizes the value VI, the I of P, and we define the induced game for that scenario where we take only those mixed strategies where the utility, the expected utility of a player is greater than the value V. Right? Now, this induced game, so this set is compact and convex, so it has a Nash equilibrium. Look at that Nash equilibrium, take your strategy. This will be your strategy in the cooperative equilibrium in the original game. So that's the idea. In a bit more detail, how do we compute the probabilities and the payoffs? So I need to give you these 4 numbers for 2 scenarios, PS and PC. So for PS, we know the probability, 0 and 1. For PC, we start in the iterative setting. We start with just completely fictitious play with probabilities half for each scenario, cooperative or deviations from cooperative play. Now, if player I observes cooperation in the first round, then the probability of PC grows to 2/3. Otherwise, it drops to 1/3. And in general, if before round T we observe K cooperative plays, then the probability to play cooperation in round T is given by k plus 1 divided by T plus 1. Now, by cooperation, we mean here cooperation with respect to the corresponding induced game. So we look at the previous stage, we look at the only those strategies who are supported by the induced game, right? And now for the payoffs, if we look at the game, which is either Prisoner's Dilemma or Traveler's Dilemma or the public goods game, then it has a unique Nash equilibrium, and it also has a unique Pareto optimum. Yeah?
What happens if the socially optimal outcome is individually the worst possible outcome for a player?
Well, it's not socially optimal, it's Pareto optimal.
So it could be that kind of somebody selects a cooperative equilibrium where his payoff is, let's say, the worst at the table. In theory, at least.
How can it be the worst in the table? No, it can't be.
No? Wait.
It's Pareto optimum.
Ah,
Pareto.
Yeah, it should. Yeah, sorry. It's Pareto is not there. It should be there. It's not social. It's not the social welfare optimal. It's Pareto optimal. And in these three games, the Nash equilibrium is unique, and the Pareto optimal profile is also unique. Okay, so the payoffs of the agents are well defined in these two settings. And so we define the payoff for the selfish play as the payoff of the agent when he plays a Nash equilibrium. And since the probability for that play is 1, this is also the value of V for that scenario. For the cooperative scenario, the payoff of the agent will be given by his payoff in the Pareto optimal profile. Okay? And the only value that is remained is the payoff of the agent when he expects a cooperative scenario, but there are deviations from that. In the first stage, this payoff is given by the infimum payoff when he looks at all the profiles where other players have individual deviations, but he is stuck with the cooperative play. All right? So he looks at all the sigmas where the strategies of the others are weak improvements with regard to the optimum plays, Pareto optimal play, but he plays this particular strategy. And for next iteration, for the next iterations, we just take the average strategies played by the other players, and we fix our player to play the optimum, the Pareto optimal strategy. So this will give his payoff. So this gives us the values of V. We take the maximum one, either for the selfish play or for the cooperative play. We define the induced game, take the Nash equilibrium of that game, and the strategy of each player as the Nash equilibrium strategy in his induced game. This is how the cooperative equilibrium is combined. Okay, let me just show how it works. For Traveler's Dilemma, we played with claims between 80 and 200. There were groups of 10 or 12 subjects, and they played 10 rounds of the Traveler's Dilemma with either low penalty of B, 5, or intermediate 20 or 25, or high 50 and 80. And they were casually matched after each round. So in the original paper, as I mentioned, there is also the prediction model of called learning logic model, which is basically just the quantal response with probabilities calculated using the logic functions. The differences between the two concepts are, first of all, they are different conceptually. The first one, cooperative equilibrium, applies the idea of natural attitude of cooperation, while the learning model explains the deviations from Nash equilibrium in terms of mistakes made in computations by the players. And secondly, the learning model uses two fixed parameters, the learning parameter and the error parameter, while the comparative equilibrium doesn't use any free parameter. So it is predictive, while the other one is descriptive. Okay, so these are the data. For low penalty values, the actual claims of the players are quite high. Okay, so these are, the first column is average absorbed play across the rounds, and it's quite high, and it goes higher to the end of the experiment. And both the iterative equilibrium and the learning model actually capture this tendency, while ICE comes quite much closer to that than the learning model. So this is how it looks like. The black line is the actual data, the red line is the LLM, and the blue line is the cooperative equilibrium. For higher values of the penalty, the situation is similar. So ICE clearly outperforms the LLM, and it's very close to the actual data, especially in the very last rounds. It performs less accurately for intermediate value of B25 here, actually. LLM and ICE are comparatively the same, but also the actual data is very oscillating. So it's actually hard to see any tendency towards either high or low rewards. While the penalty gets higher, then the players tend to claim lower reimbursement, in particular in the later rounds of the game. And as you can see, for the very high penalty, actually, once again, both LLM and ICE are close to the actual data, but ICE literally coincides with the actual play, where the players, by the way, play the Nash equilibrium there. They just claim the lowest possible reimbursement. And LLM comes closer, but it never coincides with that. For Prisoner's Dilemma, we had, well, 70 subjects with playing 25 rounds of the Prisoner's Dilemma with the shown payoffs. And there were three treatments with different matching schemes. Either the players were matched randomly to play with each other after each round, or they would be correlated by one period correlation. So if they play cooperation in the previous round, they would be randomly matched between those who played cooperation as well. And the last one is weighted history correlated matching. You looked back 5 rounds, you weight with Fibonacci numbers, doesn't matter. You weight your plays in the previous rounds, and you took similar players randomly. This is how it looks. So the black one, once again, is the actual data, and the blue one is the ICE. It comes very close, in particular in cases where the matching was correlated. It's a bit less accurate with random matching. It looks, let's say, less optimistic. So the data there is the percentage of defection. Okay, so it looks less optimistic for the random matching, which you can explain by the high value of defection in the intermediate rounds of the game. So somehow, the IC gets upset, and it continues to predict higher rates of defection. For the public goods game, also there were 3 treatments with 3 different values of the constant marginal return. There were 36 subjects for the first and the third treatment, and there were 60 subjects for the second one. And they played 10 rounds of the public goods game with groups of 4. And the data looks this way. This is probably the less optimistic figure, where you can see that IC prediction, especially in the first round, is just 0, which is very far from the actual number, but it gets closer to that to the later rounds. But you can see that the standard deviation here is very, very high. So the actual data is very heterogeneous, and it's hard to predict it better than that, and, well, possible, but hard, I think. And ICE stays within the range of the standard deviation anyway. So it's not very close, but it's close, and it gets closer. The error decreases with the later rounds of the interaction. And similar picture we see for the higher values of the marginal return. So this is what I had to show, basically. So we give the notion that is fully predictive. It doesn't use any free parameters. It seems to work well, in particular, in traveler's dilemma. The predictions are very, very precise. The questions are, okay, can we make better predictions? In particular, we should tackle the cold start effect. So we started with completely random probabilities of half-half. So we probably should have done something smarter than that. Second question, what can we say about the convergence of iterated behavior? Right. So if we talk about ICE, it can converge only to the Rabin's-Fenis equilibrium, which is either the lower or higher claim for the traveler's dilemma or cooperation or defection in the prisoner's dilemma. But can the actual behavior converge to something which is different from that? Like if, for example, you would assume that actual behavior in the traveler's dilemma would converge to a strategy 175. Is that possible? So if I play if I know that we converge to 175, so my opponent plays that, I can either reduce my claim and get better gain, or I can increase my claim and show him that we both can do better than that. So it's, in fact, implausible that an actual behavior will converge at all in this situation, if not to the extremes. And the final question is how to extend this notion to other relevant games models, which are not as extreme as the social dilemmas, where you have obvious difference between the Nash equilibrium and the Pareto optimal solution, where you have sort of obvious incentive to deviate from the Nash equilibrium. Because in certain games, you may have the social dilemmas embedded in metagame, which would result in more complicated cooperative coalitional structures. Right? So then the scenario that you should consider from the beginning should be much more complicated. But theoretically, it's extendable to that. That's it. Thank you.